Dr. Umesh Gupta from Bennett University. Their insights have illuminated various aspects of generative AI from academic industry and global perspectives. Today, we are delighted to welcome Dr. Marcus, Principal Architect for Data, AI, and share his expertise.
Hello. Uh, I think Millie is having some internet issue. So I am just introducing our speaker, Dr. Marcus. So basically, he is currently serving as a data and AI lead architecture in the Unisys Automation Hub, where he help organize, utilize data and AI for hyper automation of business process. Beyond his client-facing responsibility, Marcus work on integrated new AI and automation technology into Unisys next generation solution. His previous experience include implementation AI and natural language processing NLP projects for commercial, public sector and government client in the police, defense and intelligence sector. Marcus professionally and uh, by his in-depth healthcare knowledge stemming from his work as a paramedic and involvement in international crisis management and disaster relief. He holds a bachelor in computing from the University of St. Helens in the UK and master in digital healthcare and a PhD from Tallinn University of Technology in Estonia, focusing on e-government and AI-based digital decision support system. Marcus has also made notable contribution to the academics, having published several scholarly papers in high-ranking academic journal. Additionally, he regularly speaks at conference, sharing expertise in the field. So today we have Dr. Marcus. Now, Dr. Marcus, is your hand.
Hello, am I audible?
Yeah, you are audible.
Perfect. Thank you for the introduction and thank you for the invitation. Let me just share my screen and then we can get started.
Yeah, it's visible, sir.
Perfect. So, okay, perfect. So yes, thank you for inviting me to talk today about the convergence of artificial intelligence and quantum computing. So basically about quantum generative AI and what we are doing at Unisys with quantum computing.
Hello,
Sorry,
sir.
Marcus.
Your voice is not audible.
Your voice is very low, Marcus.
Okay. Is it better now?
Now a little bit more.
Is it, can you hear me now?
Hello?
Hello, can you hear me?
Yeah, I can hear you, but your voice is very low.
Okay, let me see if I can change the microphone settings. Is it better now?
Yeah, it's better now.
Perfect. Okay. So, yes, as already mentioned, my name is Markus Bertel. I'm a principal architect for data AI and automation at Unisys. And I'm currently a lecturer and researcher at Vienna University of Economics and Business, where I mainly research quantum computing for optimization in travel and transportation industry and supply chain management. Before I get started, I want to quickly introduce Unisys because I think most of you might have not heard about us. However, we are a global leader serving over 800 clients in 50 countries worldwide with a presence in 45 countries and generate approximately 2 billion in revenue. Something which I'm very proud of is our extensive portfolio of 500 plus patents, which in my opinion reflects our commitment to innovation. And this is especially important when we talk about topics like generative AI or quantum computing, where we have a nice partnership with a lot of universities, but that's something I will touch on later in my talk. So when I started at Unisys working with AI for some time, then after a while, when the large language models became mainstream, I wondered what's next. So after artificial intelligence, what is the next big thing? And in my opinion, this could be quantum computing. So we started to look into quantum computing, which was actually pretty hardcore. We started with our computer science knowledge, but soon discovered that also good understanding of physics, mathematics, and the application domain where you want to apply quantum computing is needed. So this talk will be on a higher level, but of course, if you have questions, feel free to ask. But I'm trying to explain the concepts of quantum computing and quantum machine learning without digging into the mathematical background, because this would take us maybe 3-4 hours just for the mathematics to get us started, and that's just out of the scope. So yeah, when we started in 2022, as I said before, we started with a bunch of AI and machine learning engineers, soon hired then the first quantum scientists and physicists, because we discovered that you actually need to have this in-depth knowledge of physics to understand or really work with quantum computing. And yeah, we started our university corporations and research in the area. And I'm very proud that till today we managed to hold research corporations with many international universities like Newcastle University, University of Southern California, the National Quantum Computing Center in the UK, and so on and so forth. And yeah, we are working closely with them, supervising students, but also supervising master thesis, project works, and doing campus programs there to really make sure that we get all the input from the university sides in new technologies, but also being able to share our business expertise and knowledge and bring together basically the best of both worlds. But enough with the intro and back to the topic about quantum computing and Gen AI. So I'm going to start to talk about generative AI and then quantum computing to give you a little introduction of both things, and then we'll put it together and talk about quantum machine learning, especially two types of quantum machine learning, quantum Boltzmann machines and quantum tensor networks. So I think you have explored generative AI in detail already in this week, so I'm going to only touch briefly on that. It's obviously a type of machine learning which focuses on creating new data that is similar to what it has seen before from training data, and it differs from discriminative AI, which focuses on classifying data into predefined categories. But it's also not something new. So even though the breakthrough with GPT was only recently, generative AI has a long history dating back to the 1950s, when the first generative models were developed. Most significantly, probably the LSTM, so long short-term memory, in the 1990s, which we use basically till today. And since then, the field, of course, has evolved rapidly, especially in the last years, with the development of new algorithms and new techniques. But what we see is that those new algorithms and new techniques start to consume more data and more hardware resources, and we are kind of touching on the limits of what's possible in terms of compute power already. And this is something I will circle back later on when we talk about quantum computing. I already mentioned basically the two types, generative models, which aim to learn the underlying probability distribution of data, which makes them very suitable for using together with quantum computing, because there we talk a lot about probability distributions and energy landscapes. So we have a lot of similarities from that perspective. And while discriminative models aim to learn the decision boundary between classes, so they kind of have very different use cases, right? And for today's talk, we'll focus on the generative models and bring them together with quantum computing. So when we talk about quantum computing, then we first need to talk about quantum mechanics, which is the foundation of quantum computing, and it governs the behavior of particles at the atomic and subatomic level. The key principles, which I will explain in the following slides, are the wave-particle duality, the uncertainty theory, and the quantization of energy. And those three things are very important to kind of utilize the quantum effects to be able to get the speed up, which is often claimed from the quantum computers. So, as I said before, we are using the kind of wave-particle duality, so the assumption that everything has a wave-like nature. And the assumption that everything is quantized. So quantized means nothing else than we have a fixed amount of something. So for instance, we need to give an electron a fixed amount of energy to jump to the next energy level. And you can imagine that like different stairs, right? So you cannot jump half of a stair. You either jump the full stair, or if you don't have enough energy, you cannot jump one stair up. And the same basically we assume about quantum particles. And the last thing which I talked before is the problem or the advantage of superposition and the precise measurements. Basically, as you probably have heard, it means when we measure qubits in a quantum state, then basically they lose their quantum state and they collapse. So we have a precise measurement of quantum states, which is basically impossible. And when we now use those principles and transfer them to classical bits, which we know from information theory, so basically 0 and 1, on and off, then we can create the qubits, which in contrast can have multiple simultaneous states at once, which allows us to build up more complex computations and data processing. The qubit technology, there are many different qubit technologies at the moment, and we don't know which will be the survivor. So my guess is one of those in the end will succeed, and the other ones become kind of not important anymore. At the moment, many firms work with superconducting qubits like Google and IBM and also D-Wave. So the superconducting qubits are this chandelier-like things which you might have seen in pictures when you Google quantum computers. But there are also other types of qubit technologies. For instance, Intel uses technology which is called quantum dots. Microsoft uses topological qubits, and there are even companies which work with crystals and kind of sending photons into crystals to execute quantum algorithms. So there is really a wide variety of qubit technologies out there at the moment, all with pros and cons. And as I said before, most probably one of those technologies will succeed and will kind of be able to scale to a large number of qubits, and then the other ones will start to be neglected. But how many of those qubits do we currently have? Well, that depends a bit. First of all, which type of qubit, and then which type of quantum computing we're using. IBM has processors with approximately 500 qubits. D-Wave, for instance, has quantum annealers with already 5,000 qubits. So what we definitely can say is the number of qubits is rising drastically in the last number of years. So we see improvements both on the hardware side when we talk about the qubit technology itself, but we also see improvements when we talk about the algorithmic side of things. So how the computations are done on the qubits. So both sides are heavily researched at the moment and will be improve and improve. But why do we need this even? With classical computing, we have the problem that Moore's law is reaching its plateau at the moment. So the question is, how long can we actually increase hardware to solve problems? As I mentioned before, with generative AI, we are building larger and larger models, feeding them with more and more training data to kind of make them more powerful, right? But at some point, hardware will not be able to keep up anymore, and this point will come sooner than later. And then we have a problem, right? Because what do we do next? With quantum algorithms, this is fundamentally different, because quantum algorithms allow us to shift a problem's time complexity from super polynomial to polynomial time. And as you see in the graph on the right-hand side, this makes a drastic difference for more complex problems or problems which require a lot of computation and a lot of data. What quantum algorithms are we talking about mostly? So there is a prominent quantum algorithm which is called Shor's algorithm, which was developed by Peter Shor already in 1994. So basically, as with generative AI, also quantum algorithms are not a new technology, and quantum computing is not a new technology. This has been here for already quite some time, but we only recently see that it gets popular and that people actually start to work on that on a larger basis, right? And yeah, so Peter Shor already worked on quantum algorithms in 1994. And found a way on how to efficiently factor large integers, which in theory would make it possible to break the RSA encryption, right? Because the RSA encryption relies on the fact that it's very difficult to factorizing large integers. So this is something which was already known many years back, but the hardware was not ready back then to actually execute this algorithm, which Peter Shor developed. There was recently a research paper by, I think it was Chinese scientists, who claimed to have broken the RSA encryption. But when you read the research paper, then you actually discover that they used 10 qubits, and what they did is they broke the 22-bit RSA encryption, so not the full RSA 2048 encryption, which is used nowadays. So there is still kind of a some way to go till we are at this point where we cannot use RSA anymore. But as I said before, we have already up to machines with up to 500 qubits. So if you think that they were able to break RSA encryption with 22 bits with 10 qubits, and then you scale that algorithm to 500 qubit processor, then you see that we are getting very close to what we to the algorithms or to the RSA 2048. But we still have the symmetric encryption. However, also there, quantum algorithms are helping the bad guys to break this. And one example is Gruver's algorithm, which was also developed way back in 1996. And it provides a quadratic speedup for unstructured search problems. So basically, this means that the security of the keys of symmetric key algorithms are only half as good as now. So if you have a standard ASCII 128-bit key, then this would only be the equivalent of a 64-bit at the moment. So in terms of security, we already see that quantum computing will basically be transformational in the next years. So for all security analysts, it's Houston, we have a problem. We need to think about that and think about quantum safe cryptography, in a very short time frame, because it's not a question if quantum computing will be able to break our currently used encryptions, it's more a question of when. And then it depends on which experts you are asking. Some say it's 5 years, others say it's 10 years or 15 years, but this time will come. So it makes sense to think about that and be prepared. How is that all possible? Well, as I said before, we are using the fundamentals of quantum mechanics, namely superposition, which allows the qubits to represent numerous combinations of 0 and 1 at the same time. You can think about that like the spinning coin you see here. So if you spin this coin, then the question is, what does the coin show? Is it heads or tails? Can you say it's both? And the same is with the qubits, right? We don't have only 0 and 1 anymore, so we also have the superposition state, which is both 0 and 1, basically. And this enables them to kind of make very complex computations. The second concept which we are utilizing for quantum computing is the concept of entanglement. And this means that we can create a connection between two qubits, which enables them then to share information basically instantaneously over also a large physical space, right? And the last phenomena which we are utilizing is quantum tunneling, which allows particles to pass through a potential energy barrier, even if the particle would not have sufficient energy to classically overcome the barrier. So if you think about the hill, then quantum tunneling basically allows the particle to go through the hill, and it's not required to have the energy to go up the hill and then down the hill like we would expect in classical physics. And those concepts can be now applied in two ways. The first is gate-based quantum computing, which uses quantum gates to perform various operations on qubits. And this is very versatile for numerous types of problems. And then on the other hand, we have quantum annealing, which focuses on optimization problems by finding the lowest energy state of a problem. So quantum annealing is not Turing complete, which means it can only solve a certain type of problem. So for instance, QUBO problems. QUBO is an abbreviation for quadratic unconstrained binary optimization. And that means it's basically a combinatorial optimization problem with binary variables where we have an objective function which is quadratic polynomial in those variables, in those binary variables, right? And this is an NP-hard problem class. So this is something where we kind of can cut down on the super polynomial complexity of classical computing. Those QUBO problems are typically optimization problems. So for instance, in logistics, the classical traveling salesperson problem and things like that. Then the gate-based quantum computing is Turing complete. So basically we can give a gate-based quantum computer an arbitrary set of instructions, which represents a program, and then it will execute it. And this makes the gate-based quantum computing much more powerful because it can basically execute whatever we think of, while quantum annealing is restricted to those optimization problems. So for this talk, I will focus on the gate-based quantum computing because this is a bit easier and also used a lot in quantum machine learning. For the quantum annealing, we would need a completely different mathematical concept, and that's a bit out of scope for this 1 hour talk, which I have today. So when we look at gate-based quantum computing, then we basically have a quantum computer. The quantum computer is the computing device which gets an input. And obviously we expect an output like the result. The input in this case is our quantum gates. And with the quantum gates, we build those quantum algorithms. So in that case, you see that we have here 1 qubit. We apply gates to put it into superposition, and then maybe get my laser pointer. So here, this is the notation for a qubit. Then here we have the automat gate, which puts this qubit into superposition. And then here we have a measurement gate, which takes this qubit and measures its states. And then you see here those 2 lines, which basically mean that now we get the classical output. So kind of a binary output, 0 or 1. And when we take now this quantum algorithm, this very simple algorithm, give it as input to a quantum computer, then we get the output 0 or the output 1, both with a probability of 0.5, right? Because we have the superposition, and in the superposition we have kind of both states, and when we measure it, it collapses. With that, we can now play a coin game. If we say we have a fair coin, and the 0 state of the or the head states represented by 0, tail states represented by 1, and then the game works in the way that you have a fair coin in a head state. The computer decides if it flips the coin. Basically, then you decide if you want to flip the coin or not. And in the end, the computer decides again, if it flips the coin. And then if it's tails, you win. If it's heads, the computer wins. If we would execute this or program this game on a traditional computer or machine, then the outcome would be 50-50, like approximately. You have a 50% of winning. However, if you program that on a quantum computer, and you can actually do that, I show you later on how this works, and you can implement this. And you implement this game, then actually the computer wins in 100%, nearly 100% of the time. And how is that possible? Well, that's possible because the computer can put the coin into superposition, right? So then it has the states of both heads and tails, and it doesn't matter if you flip the coin or not, you're not going to change the superposition. So you can imagine this like a fluid. It doesn't matter if you steer the fluid, it's still the same fluid. The steering doesn't change the fluid itself, and the same is with the superposition. So if the superposition is, or the coin is the fluid and the steering is the flipping, then you see that it actually has no impact. And in the end, you can apply a gate to get the coin from a superposition to 0 or 1 state, and this makes the computer win in all cases. I promised to show you how you can implement that, and this is possible with many different techniques. As I showed before, there are different qubit techniques from IBM and Microsoft and Google and so on, and they all have some libraries which you can use to kind of interact with their quantum computers. I used here the IBM Q, so the quantum computer from IBM, which uses the superconducting qubits, and the library which is called Qiskit, and the Python programming language. And this is what we internally found as very useful and very usable library to get started with quantum computing. And then you basically start your Python development environment, and you write your code. So you write how many qubits do you want to have in the beginning, then what gates are you applying to that qubits, and in the end you measure, and then you get the result. And based on that, you kind of program your algorithm, and you can execute that on real quantum computers. IBM even gives away, I think, a few minutes of quantum computing time every month for free. So you can run that, and you can basically try this out yourself. Here, a quick screenshot of how this looks like with the IBM Quantum Composer. You see you have on the left side all the different quantum gates. And as we know from the traditional gates, there are like AND gates, OR gates, NOT gates, XOR gates, and so on and so forth, plus different gates for quantum functions like the Hadamard gate. And based on that, you can build your algorithm, which you see here. So you can either use drag and drop and just put the gates to the qubits. Here we have kind of a 3-qubit system, and you can also use here Python and Qiskit, or you can select another library to program in and write your code, and you will then see a graphical representation of your quantum algorithm. You see the probability distribution and you see the state vector. So this is kind of very useful tool to get started. You just need to go to quantum.ibm.com/composer and log in with IBM ID, which is free of charge, and you can use the system. So if we now emulate, or if we now just look at flipping of the coin. So for simplicity, if we break the example from before down to just flipping the coin, then you see that you have here 2 states, right? So you have the 0-0 state and the 1-1 state. If you look at the gates from that, then you have here the 2 qubits. You put the qubit into superposition, then you entangle the qubit, you measure the first qubit, you measure the second qubit, and because they are here entangled, you will all the time get the same result. So you only get the 0-0 or the 1-1, and you don't have this 0-1 states or 1-0 states because of the entanglement here. Right, we could also apply other gates, but for simplicity, I just wanted to show here the simple example with the 2 qubits and the classical bit, which is 0 and 1 as an output. The Hadamard gate here, which puts the qubit into superposition, the controlled NOT gate, which entangles the 2 qubits, and then the measurement gate for measuring qubit 0 and the measuring gate for measuring qubit 1. I talked a lot about positive things of quantum computing and what it all will be able to do with the breaking the encryptions and so on. But of course, quantum computing also has some challenges. And I divided that into 3 categories. The first thing is we have measurement errors. So when we measure a qubit, then it collapses into a 0 or 1 state, which is with high likelihood the correct state, but it not all the time does it because of problems with the hardware and so on. So when we run the experiment before on a real quantum computer, then we actually get this output. So most of the time we have 0-0, and most of the time we have 1-1, but there are some measurement errors where we get the 0-1 or the 1-0. So this graph shows that the error correction is still needed and that there still are some errors if you run a quantum algorithm. Then we have hardware errors. So as I said before, if you look at the superconducting qubits, for instance, they need to be cooled down to very low temperatures, and sometimes this doesn't work, or the qubits are interfered with from the outside because they are very fragile. It can lead to errors, and then again we have a problem with the algorithm and we don't get the output. And the last category of challenges in quantum computing are software errors. And that is very important because programmatical mistakes in quantum computing algorithms are actually the majority of errors which we are currently experiencing. And that means that simply the algorithm is wrong. And why? Because the implementation doesn't meet the specification. So as I showed you before, you need to break down your algorithms on a gate level. So this makes it very complex if you have larger algorithms, or if you talk about quantum machine learning and so on. And often there are just errors in it. You miss a gate or apply the wrong gate and so on, and then the quantum algorithm doesn't work as you would expect it to do. Nevertheless, we have working examples where we applied quantum machine learning. One of that is our logistics optimization solution, which I have been working on the last year. And this is basically the first and only quantum annealing solution which is currently in production. So we are very proud that we are the first ones who partnered here with Malaysian Airlines and got the optimization of cargo loading into aircrafts implemented on a quantum computer and executed in production. And this is kind of very how to say, like a very breaking thing, because if you look at the complexity of algorithms in the logistics space, then we deal with a number of combinations which are simply not possible to compute with classical computing techniques. So if we just look at this example here, then we ran a logistics routing problem on a quantum annealer with 50 nodes, and basically 3 vehicles. So, this traveling salesperson problem, basically, or scheduling problem. You have 3 vehicles, 50 nodes where you need to get those vehicles to, and how do you schedule that? And if you compute that with traditional methods, then this takes about 7 years, because you have 2 to the power of 630 combinations. But if you implement that on quantum computing, then you have a speed up which equals to about 7 seconds. And yeah, here you can see the different applications of this logistics optimization. So first of all, the bin packing, we're basically optimizing on how the different parcels could be loaded into the airplane. And the tricky thing is the airplane is not square, but you have this kind of triangular thing here because of the body of the airplane. So that makes it very hard to compute. And you have the package route optimization, which I discussed before, where you need to kind of calculate the best route for your vehicles. You can have a look at all that in detail if you Google for our paper, Performance of Commercial Quantum Annealing Solvers for the Capacitated Vehicle Routing Problem. And there it's described in detail how we applied quantum machine learning to optimize this. It would be like way too long to explain it in this talk, but if you have a look at the paper, then you see, and you can actually also try out yourself how that works. Now, what I also want to highlight is why were we able to get this success at the first quantum machine learning solution in production? And this is not only because of the quantum hardware, but also because we have 4 decades of training data, and we designed a quantum algorithm which can be applied to that training data. So the key points to take away is that quantum computers are not just faster computers. This is kind of what's sometimes explained, but it's just wrong. The thing which makes quantum computing so extremely fast are the quantum algorithms which utilize this kind of quantum physical principles which I explained before. And if you just have the quantum computer and execute a normal algorithm on the quantum computer, then you will see no improvement. So you need to have the quantum algorithm, and that is kind of the special soup here. So yeah, if no quantum algorithm provides a speed advantage to a problem solution, then there is no point in using a quantum computer. So quantum computing is a fundamentally different way of computing. So when you apply it, then you need to think about three things. You need to have the data. So quantum computing doesn't solve the problem of classical machine learning. You need to have high quality data and large amounts of data to be able to train your quantum machine learning models. You need to have the quantum algorithm, so you cannot just use the normal machine learning models and execute them on the quantum hardware. And of course, you need the quantum hardware, which is big enough and has enough qubits to execute this algorithm which you designed. And only if you have those three things, you get the quantum success. Yeah, so if we touch now briefly on the algorithms of quantum machine learning, and again, this is just an overview of two quantum machine learning algorithms which are out there. There are many more, and it's just a high-level overview because as soon as you start digging deeper, it gets complex very fast, and it gets very mathematical and very hard to explain using PowerPoint slides. So the principle of quantum machine learning is basically that we use models which we know from the classical machine learning, but we map them to quantum algorithms, and this allows us to leverage the speed up and provide this significantly faster processing speeds compared to the classical algorithms. So this means we're able to handle larger data sets for the training, which overcomes this challenge of the LLMs, for instance, which we are facing now, that we cannot put all the data for the training which we would want to train on because it would just be too large and require too much computing power. So because the quantum computing can handle that, because one qubit can represent more than kind of one data point with the superposition. And as I said before, we are basically mostly at the moment leveraging standard machine learning models and map them to quantum algorithms. So what you will see when you Google quantum machine learning and when you search for a paper in that space is that you find something like quantum support vector machines or quantum neural networks or quantum restricted Boltzmann machines or quantum variational autoencoders. So fundamental idea of how the machine learning works is the same, but we use the quantum part to speed up the computations and make sure that the models can kind of utilize more data. So yeah, as I said before, those are the three things which give us this quantum advantage when we talk about machine learning on quantum devices. The restricted Boltzmann machine is now an algorithm which we work quite a lot at Unisys, and it is a type of generative stochastic neural network that can learn a probability distribution over its set of inputs consisting of visible and hidden units. And we'll now have a look at the standard restricted Boltzmann machine and then at the quantum restricted Boltzmann machine. So as I said before, the quantum restricted Boltzmann machine, the restricted Boltzmann machine contains of two layers, visible layer and a hidden layer, and all nodes of the visible layer are connected with the hidden layer. So what makes the restricted Boltzmann machine restricted is the fact that the hidden layer and the visible layer is not interconnected. So we don't have connections here or here. And this is because it would require a lot of computing power to train that. So people said, okay, we'll leave it out and we do it in a restricted way. And this is basically the restricted Boltzmann machine. The RBM is trained using something which is called contrastive divergence, which allows RBMs to learn from unlabeled data. And then they can be used basically for feature extraction, collaborative filtering, or also dimensionality reductions. And the main problem with the RBMs, with the classical RBMs, which we are facing, is the efficient training. With the training efficiency. So while the RBMs are kind of efficient, the Boltzmann machines itself are very complex and don't scale very well, especially in large data sets. And this is where we can now apply the quantum part and the quantum restricted Boltzmann machines, which now work a bit differently. Yeah, I see there is a question of if the recording will be shared, and I think the recording will be shared, yes. So yeah, the integration of quantum computing allows the restricted Boltzmann machines to leverage the superposition and parallelism in the computations, which allows these faster training times and better performance on more complex data set. And unlike the classical RBMs, classical restricted Boltzmann machines, they utilize the qubits, which change the nature of data representation and processing compared to the classical bits, because you can represent more data with 1 qubits. And this can be applied in many different areas like finance, drug discovery, basically everywhere where you process large data sets and kind of need to model this probability distribution of data, like optimization problems, for instance, like we saw before with logistics. We also used restricted Boltzmann machines quite successfully, or quantum restricted Boltzmann machines quite successfully on dataset balancing. So we trained the quantum restricted Boltzmann machine on imbalanced dataset from intrusion detection systems, approximately 1.6 million data points. And then we used the QRBM to generate data from the minority class to get to a balanced data set in the end, and showed in that paper that actually the classical classification algorithms can be drastically improved with these dataset balancing methods compared to other balancing methods. But again, you can have a look at the paper and we explain there step by step how that works. We explain the algorithm, yeah, you can basically also use the code we show there and try it out yourself. The last quantum Gen AI network which I want to touch today is quantum tensor network, which got very popular. So tensor networks are mathematical structures which are used to represent complex quantum states. And they have basically become very crucial in quantum physics and computational mathematics to model quantum effects on a very, very large scale. So you can imagine a tensor network as interconnected tensors where one tensor represents a quantum state, and each tensor basically corresponds to a multidimensional array which allows the representation of large systems in a compact form. The difference between the normal array, which we know from programming, and the tensor here is basically, at least if I put it to simple terms, that the tensor makes use of hardware acceleration to improve the computational speed here. So it's kind of faster than a normal array, and that is why we talk about tensors here. And yes, so as I said before, it emerged from quantum physics and statistical mechanics to kind of being able to simulate or simplify the simulation of those many-body quantum systems. Yeah, I guess I jumped now over a few slides because I'm a bit behind the schedule, and get to my sum up slides so that we have some time for questions. To sum up, quantum computing is ready for business. You have seen that it can be successfully applied in logistics. So we have that out in the market. If you Google Unisys logistics optimization, you will find the solution, and you can have a look at yourself how it works and what it basically does. Even though it's the first solution which uses quantum machine learning at the moment, I'm sure that in 2025 we'll see a lot more quantum machine learning solutions which will come to market. Remember that quantum computing is a fundamentally different way of computing. So it's not the quantum computer which will improve your computation in the end, but it's the quantum algorithm. So you need to have the algorithm, and you need to have the data for the quantum machine learning. And if you don't have the data or the algorithm, you won't succeed with quantum. I talked about encryption and about breaking encryption. You also see here on the numbers that the quantum computing market is rising. And then I put a QR code here. If you scan that, or if you scan it in the recording, then you get to our Google Scholar page where you find all the research papers which I showed you and many more. So you can have a look at, we have tutorial papers out there with the examples which I mentioned, and you can have a look at them and work on them yourself on the IBM Quantum Composer to try out what I explained on a very high level today. I really hope that this high-level overview was helpful. As I said before, you can only scratch on the surface, because as soon as you start to dig deeper, quantum becomes unbelievably complex, and you need to spend months, if not years, to kind of explain the mathematics and the functionality of the hardware and so on. So this is really a complex research field, but I think a very fascinating one. And with that, I want to thank you for your attention and open up the floor for questions.
Thank you so much, sir. Participants, is there any question from your side? Participants, is there any question? Yes, anyone have any question? Okay, I have a question, sir.
Yes.
Sir, is there any ethical implications of quantum computing in the field of AI?
Yes. So there definitely is. We have submitted a funding proposal for applying quantum machine learning to discover new drugs. Because as I said before, the Groover's algorithms can be used for search problems, and you can use networks to model the protein interactions of new drug candidates. So this would allow you to, for instance, find new therapeutics very swiftly. And that, of course, has a lot of ethical implications. Like, what do you do if you find a new cancer medication, for instance? You need to run it through the clinical trial, but you know from the quantum simulation that it works. So can you already give it to patients? How do we need to adapt our current ethics board reviews when we talk about clinical studies? So there are a lot of implications. There's also a lot of implications when we talk about data protection, because of the fact that many ways to protect our data at the moment are based on the assumption that it is very hard to do certain computations, which will be much easier with quantum computing. Yeah, so there's definitely a lot of ethical things to consider. I hope that answers your question.
Yeah, sir. Thank you so much, sir. Any other question? Anyone have any question? Okay. Sir, one more question from my side. Sir, is there any different algorithm rather than the Shor algorithm of the quantum computing that is suitable for the machine learning field?
Sorry, can you repeat the question?
Yeah. So my question is that there are the various algorithm of the quantum computing, like as a Shor algorithm is there. So there is any other algorithm for computing all the things same as Shor or better than Shor?
Yes. So the Shor algorithm itself, as I said, is very old, and people have been working on the algorithm all the time and improved it and changed it a bit. So the what we call Shor algorithm now is actually not the original algorithm which has been developed by Peter Shor, but already like an improvement. And there are many more of those algorithms, especially when we talk about quantum annealing. I think there is a lot of implications for machine learning, because if you think about training neural networks, then you basically are faced with an optimization problem. And the question is, how do you phrase this optimization problem now in a way that the quantum annealer can understand it? And if you manage that, then you could use the quantum annealing, for instance, to train neural networks. So there are, I think, a lot of different algorithms which could be used for machine learning. Yeah.
Okay. Thank you, sir. One more question from the participant side is that what are the primary challenges in implementing the quantum algorithms for generative AI? What are the primary challenges in implementing
Yes.
quantum algorithms for generative AI? Yeah.
So I think the primary challenges are on the one side, definitely the complexity of quantum.
Yeah.
So I showed this Venn diagram in the beginning, and I think you really need to have an interdisciplinary team if you want to successfully apply quantum algorithms for generative AI. So you can, of course, use Qiskit or something like that, and then you just call the functions like you do with scikit-learner or so on. So you don't go deep into the Gen AI space. But if you really want to look what's behind the functions, then you need to have someone who has a deep understanding with physics. You need someone who has a deep understanding with mathematics and the Gen AI space. And you probably also need someone who has a deep domain understanding so that you can actually formulate the model which you want to solve using quantum computing. The second challenge, which I see, is definitely a hardware challenge. So now we are getting into slowly into an area where we have enough qubits to actually do quantum machine learning or generative AI with quantum computing. But it still kind of needs to improve, and we still need more qubits to run more complex models or train more complex models. However, I'm sure this will be there in the next like 1 or 2 years. So it's not, far away. But if you want to start now, then definitely that's a challenge which you need to think about.
Yes, sir.
And
Definitely.
yeah,
Yeah,
those are,
sure.
I think, the two main points.
Yeah, definitely. Yes, participants, any other question from your side? Okay, sir, there is no other question from the participant side. So I think all have done. So Miss Millie, please
Yeah.
come.
Dear participants, if any question, you may ask. Okay. Thank you, sir. Thank you so much for your for such an enlightening session. Your expertise has made this session incredibly engaging and insightful, leaving us with valuable knowledge and inspiration to explore further. Thank you, sir. Thank you so much.
Thank you for the invitation.
Thank you, Marcus, sir. Thank you.
Now, I would like to introduce our next distinguished speaker, Ali. Is a PhD candidate in AI-based frameworks. Hello, yes, ma'am. Hello, am I audible?
Yes, Millie. Yeah, you are audible. Please continue.
Hello. Uh, okay, let me introduce
Your voice is not audible, Millie.
ATAL University of Point of View.
Your voice is not
Hello,
audible.
ma'am. Am I audible?
No. You are not audible.
Yes, ma'am, you are audible, clearly audible.
Hello,
Your
I'm
voice
audible.
is breaking. Now you are audible, Millie.
Yes, ma'am,
Okay,
audible.
okay, ma'am. Okay. Okay, let me start again. Ali Wala is a PhD candidate at Tallinn University of Technology, pioneering AI-based frameworks for motor functions assessment to improve diagnostics and rehabilitations for neurodegenerative diseases, including Parkinson's, with a multidisciplinary background.
Sorry everyone, I think Millie is having some internet issue. So I can just introduce our guest today. Speaker is Ellie. So Ellie Walia is a PhD candidate at Tallinn University of Technology, pioneer AI-based framework for motor function assessment to improve diagnostic and rehabilitation for neurodegenerative disease, including Parkinson with a
Am I
multidisciplinary background
audible?
in engineering physics, applied mathematics, and computer science. So Ellie bridges the gap between advanced technology and practical healthcare applications. So her contribution extended beyond research with a focus on teaching and mentoring in artificial intelligence and machine learning. Presentation at international conference and collaborating with healthcare institute to translate innovative research into impact clinical solution. So, uh, key contributions of LE is like developing machine learning model for diagnostic, achieving benchmark accuracy on real world data set, publishing in leading journal like the International Journal of Medical Informatics and Biomedical Signal Processing and Control. They taking a lecture in a university delivering course on deep learning in healthcare, machine learning, and applied mathematics. So, as now, Ali, this is you can just share your screen and
Oh, yes,
start.
thank you. Thank you for
Thank
the
you. Thank you so
introduction. I
much.
hope you can hear me. I
Yeah,
will share my presentation
yeah, please,
in a
please.
second. Okay, it asks me to quit and reopen WebEx. Is it okay? 30 seconds, I will come back.
No problem, no problem. You can do it.
Hello, I'm back. So hopefully it will let me share the screen.
Yeah, please share, ma'am.
Mm-hmm.
Please share your screen.
Can you see my screen?
Yeah, it's visible.
Perfect.
Yes, perfect.
Perfect. Yes. So thank you so much for the introduction. I will do a quick introduction as well for regarding my doctoral thesis, which is finalizing this week actually. So we have been working with a variety of different machine learning and deep learning algorithms and transformers type algorithms that are very popular in natural language processing is very intriguing topic. I hope I can give you some foundation and intuition. However, there's so many pieces to put together, so hopefully you will leave in somewhat satisfactory that I will gain some valuable insights. And we will talk about, yes, what goes on inside of transformers. However, a quick just introduction what we have been doing for these past several years in our lab. So I am analyzing human motor functions. And to do that, we have to kind of digitize current practices. So at this stage, if you go to a neurologist, they will ask you to fill out some drawing samples or write something and kind of test your fine motor skills in terms of diagnosing Parkinson's disease or other neurodegenerative diseases. And what we did is we kind of developed an application that will collect these signals, and we can derive much more information than just drawing. We can calculate the velocity of the handwriting, we can calculate the higher order derivatives, we can calculate different geometry between slope angles, etc. Of course, the pressure applied on the surface, and of course, the orientation of the pen is also calculated. So, okay. And why do we need this kind of precision or scaling of neurologists' abilities? Well, first of all, the diseases are very tough for the patients and for the caregivers. And the earlier we discover them, the easier will be, and the more quality of life there will be. But for example, if we look at this drawing, so we can somewhat maybe see some kind of tremor or some other symptoms that are present on Parkinson's disease, and some kind of shakiness, right? And well, neurologists could potentially see through that, but it's very hard to diagnose that just based on the drawing. It's in Estonian, so the left one is sorry, I didn't change that. The left one is a healthy patient, a healthy control, and the right one is a patient. So this one is a patient. So, but based on these drawings, we cannot decide who is who. So we need to dig deeper. And that's what we're basically doing. We're engineering new features for our machine learning models. We try to use kinematics, as I mentioned, velocity and these kind of features. Also, we use drawings, but we try to go a step further, not just 2D drawings, for example, 3D drawings that incorporate these kinematics in themselves. For example, velocity will be based on color, or color will be based on velocity, and the voxel, or the volume of the pixel, is in 2D, so voxel will be based on pressure, right? So this is the research that I'm doing, and we have developed very precise models, and well, precise in terms of state of the art, so they're kind of benchmark, above the benchmark, and also interesting and novel feature sets to include in the diagnostics. Well, briefly about the research that I'm doing. But today we're going to talk about, well, artificial intelligence type of algorithms, and in particular transformers algorithm. But I wanted to kind of give an introduction, where are we now, and what was before that, because we're talking about AI now, well, everywhere. Like every second person that I talk to is somewhat of an expert. They're applying AI in some sense, or using or researching. Well, it's everywhere. But is it like a new topic? No. We have computer scientists have been developing self-learning models from 50s. There's a Samuel's checkers playing self-learning program, and perceptron, which is the basis of neural networks on neuron, was already introduced in 50s. So why are we talking about AI now in the, well, last 3-4 years? It has boomed a lot. So there's a couple of reasons and milestones that I would like to point out. First of all, the amount of digital data is has grown exponentially, and in addition, we have these graphical processing units and the hardware that supports these kind of deep models that we stack on each other and go a lot more resource heavy, right? And the famous paper from Stanford that include the famous library called ImageNet. I don't know if the WebEx allows to raise hands, and if I can see them. I would like to ask some questions, but I would really appreciate some feedback, but I don't know if that's possible. Anyway, just a second. So the ImageNet library is somewhat, okay. Or do we go back? Okay. So this was published by Stanford researchers, and it allowed to grow of these convolutional neural networks algorithms that were used to detect objects in the image. So it included millions of images, labeled images, and combined with graphical processing units, it kind of blew up the space of convolutional neural networks and deep learning and object or image classification as we know it. And of course, today we're going to talk about another important milestone that was introduced in 2017, and we know it as a new architecture in terms of how we process sequential data, in particular text. So if before that we kind of processed it word by word, so now transformers allowed us to process it more in parallelized format, and of course in combination of GPUs it kind of blew up the space. And you probably are familiar with these powerful large language models, and transformers are incorporated in these models heavily, even in the name of the models like GPT. It's generative pre-trained transformers. So this paper is actually the basis of this architecture and kind of the first where the transformers were mentioned. So 2017, as I mentioned, and the authors are mostly from Google Brain team. It's a very cited paper, hundreds of thousands of citations, so very important paper in the field. And the basic idea what the paper answers is what part of the input should we focus on? So they introduce this kind of notion of attention. And my question, I don't know if I can see the answers, but how many of you are familiar with the notion of or concept of self-attention? I'm not sure if there's hand raising. No? Maybe someone can answer audibly if anyone is familiar. Or answer in the chat. No? Can't see any reactions. Well, anyway, the paper kind of solves the problem of processing input and leading the focus on specific important information. And this is very important in terms of understanding context, right? Let's say we have this sentence, please don't put the coffee mug near the computer because it can spill and damage it. So it is mentioned twice, and how do we know which is more important, and how do they what relationship do they have? And this is solved by this paper, and the practical use was already seen after 2017 introduction of the paper. If you maybe noticed, at some point Google search became more intelligent, and before the introduction of transformers, the query was, for example, Brazil traveler to USA need a visa, and the value was output. The output was kind of similar words in kind of similar order. But after the introduction of transformers, it became much more context. It understood the context more in depth. It understood that two has a direction, right? And the output was much more intelligent. So very important topic. Before the transformers, and actually nowadays the LSTMs and long short-term memory or gated recurrent units, the type of recurrent neural networks are still used. They are less resource intensive and computationally expensive, but they have a series of limitations that transformers will solve. We'll see that in a second or in a minute how. So they have no parallelization. With RNNs, we just put words one by one, process words one by one, and the long-term memory is an issue because if we come close to the end of the document, the beginning starts to get fuzzy, and these kind of limitations kind of made it not as good as transformers, and transformers is now definitely a state of the art. So, but recurrent neural networks are still used. There are a lot of reasons to not jump to the resource-heavy transformers. Test out with some simpler algorithms. So the tasks that transformers can solve or used in, for example, voice to text, right? So text to speech, other way around. Basically sequential data, right? So it can be images, it can be images are also can be in sequential format if we split them, and also text. Translation, which was the basis of the paper, the attention is all you need. They solved or showed the application of the new architecture on the translation task. But today we're going to focus on the generation of a next or prediction of the next word, which is kind of what large language models are doing. So they output a distribution of the words that will be probably next one in the sequence. And transformers are great tools to solve that task. A little disclaimer, I am a big fan of Grant Sanderson, who is an exceptional educator, and he's an author of a library called Manim, which is a Python library that helps you to do these kind of visualizations. I'm a big fan of the library. I have many visualizations, but this some of the videos are kind of borrowed from him because they're quite new, and he gave an excellent lecture on this topic. And this is an example of input and output, right? So the input is some sequence, and the output is basically the distribution of the words. I can want to. It's a bit. Yes, so let's do it. Wait. What I want to show is that distribution of the words is based on the probability, right? So what is the most probable word in the next sequence? However, as you can see, the most probable is not always the one that gets picked, right? Sometimes it's less probable. So are you familiar with the term of temperature? Anyway, okay, yes. So this is what is regulated by the temperature, and we will not dive into so much into these smaller how do you say concepts, but I just wanted to show that why it was jumping through it, because you can kind of regulate it with the temperature if you want your model to be like more creative and not just pick the most probable word, which could be a very, I don't know, too like exact, deterministic, and be more creative. Then you can adjust the temperature. So the 0 will be just the most probable word. But this is an introduction that what are we going to focus on? This is the task that we'll try to understand how it works behind the scenes. If you read the paper, or if you have read the paper, then you will see this kind of architecture, and we will dissect this architecture well, by parts, right? So as I mentioned with my research, we have to figure out the ways how to show the data to our models. So is it a numerical format, like these features and kinematics, or is it in a image format? But in every way, we have to encode some kind of numbers that we can use calculus afterwards in these deep layers, right? So we have to figure a way how to embed words into numbers. And tokenization comes, and word embeddings are the words that are used in this domain. Again, I'm trying to. Yes, exactly. Yes, the temperature is adjusted. The creativity like scale is adjusted. Exactly. Thank you. So tokenization and word embeddings come into play, and this is a very broad field, right? It was before the transformers. It's a natural language processing field, and it's not just related to deep learning. So the word embeddings and how the words. What are the relationships among the words? So this is very interesting and fascinating field. However, let's start with tokenization. So we have to like split our sequence in some parts. And as I mentioned, images and audio waves and audio files can also be split in some tokens, right? So it's not just for the text. Transformers work for other type of data as well. But okay, so suppose we have this sentence that quick brown fox jumps over the lazy, and we want to predict the next word, right? So one way would be to tokenize by words or tokenized by some subsequences. And my first question is, why not characters? You can write in the chat if you want, but give it a bit time to think. So why not characters? Because this is an atomic unit of a word, right? So why shouldn't we use characters? So there's are several reasons. If we will go further, we will see that every token has a lot of computational matrices and parameters that it will be associated with. So if we make it even smaller, then the sequences will be too long, and well, it can be done, and well, compute is also growing, the power of the compute power. However, it's not as efficient as words or subsequence in this case. But in practice, we don't use words as tokens. We the more like sweet spot is kind of dividing by these subsequences. Why not words? What could be limitations there? So one of the reasons, the big reason, is that well, we can't incorporate every word. Like there will be a lot of unknown words that we have to always add, because there's so many words to add. So it will be easier to kind of think in subsequences, and the easier or the smaller reasons are typos. Right? If you make a typo, then already it becomes a new word. So it will make additional computations that are not relevant. And there are languages that have no spaces. So it will be, again, a bit tricky to tokenize by spaces between words. So for this reason, the most common way, or this is a sweet spot, is to kind of divide our sequence, our sentence, into these common subsequences of three-letter tokens. What happens next, right? So we have these, okay, for the simplicity reasons, I left words, but I just wanted to mention that we usually don't use words as tokens, but just to make it more visual. So now we have to kind of embed some kind of information to these words, and we use numbers or vectors in this kind of sense. The original paper used 512 size dimensions vectors. And what does it mean? So again, hopefully it will work. Word embeddings is another topic that we can discuss for several hours, but this is a nice presentation or visualization of a word-to-vec model, for example, that incorporates information for different words. And what I wanted to show is, for example, if we pick a word rock, right? So this model embedded information about this rock in these dimensions, 200 dimensional vectors. We can't visualize 200 dimensions, right? But we can get some kind of intuition from these 3 dimensions. So what is interesting is that similar words kind of point in a similar direction, and some ambiguous words have also ambiguous relationships. For example, rock can mean a style of music, or it can mean something from geology department. So these kind of similarities kind of are embedded and trained. These embeddings are trained to have these similar dynamics. And you can use either, in the practice, the word embeddings can be trained from scratch, like you want to train your own word embeddings, or you can use pre-trained word embeddings and use these inputs in your model already that have these kind of semantic directions, right? And this is an interesting paper that I wanted to show the visualization of. So here we can see that you can draw a relationship in terms of vectors. And there was a paper from 2013, I believe, from I don't remember but I can link it afterwards, that showed that if you pick a vector, word embedding of a man and a woman, and you subtract from king, subtract man and add woman, that would be somewhat similar to the word, or somewhat distance-wise to the word queen. However, we'll put it a bit backward. As you can see in practice, actually, they are not quite the same distance, because a word queen can mean not just a female version of a king, but it can also be as a queen in terms of rock band or the band, right, musicians. So they're not quite there. However, if we look at the other examples, for example, uncle and aunt, or niece and nephew, then the similarities were much better. And you can say that some directions, as you can see, the arrow points in some direction, are responsible for gender. Some direction are responsible maybe for race and these kind of features. And if you think about it, there's no limitation in terms of dimensions that we can have. We can only visualize 3, right? But the dimensions, 512, but there are 12,228 models that have these kind of embeddings with these kind of large vectors. So, and these kind of directions of the vectors in terms of this vector space are incorporating this semantic representation, and that is what we're using as an input. Let's go further. Another interesting paper or the write-up that was introduced by DeepMinds. DeepMind is a very important lab, right? It's managed. Google is already like bought it, but they were independent at some point, and they won a Nobel Prize for their model on AlphaFold for predicting 3D protein structures. Anyway, they're doing a lot of machine learning and deep learning related research. And one of the interesting findings was, or the questions that they wanted to solve, we take the same architecture, and we kind of have these attention blocks, which we will discuss further, and multi-level perceptrons or feed-forward neural networks, which is basically neurons stacked in a network, basic neural network foundation. I believe you had the seminar already. So if you look at them and think, where are the factual information stored? Like, is it in the attention blocks that we know that we can extract facts? For example, if we say that Cristiano Ronaldo is what sports does it play? So if the network of our architecture can produce an answer, soccer or football in Europe, where did it come from? Did it come from the attention blocks or transformers that we were going to discuss, or the weights from the last layer? And what they discovered is that multi-head attention, or the transformer-based architectures that we're going to talk today, or talking already, they are storing more of a contextual and the relationship of the words. But the general knowledge will be stored by the weights of the feed-forward neural network or multi-level perceptor, in other words. So this was an interesting paper I just wanted to share. I just encountered it and read it, and it was quite fascinating. Next, what we're going to discuss is that these kind of blocks are basically stacked. So it's not just one block and, oh, it already knows the context and already knows the general knowledge. No, there are many, many blocks just stacked, and we are processing these inputs through these layers. For example, in the paper, there were 8 of these multi-head attentions. So there are a lot of layers to go through, and GPT-3 had, for example, 96 different layers of these kind of architectures, transformers, attention, and neural, just general, feed-forward neural networks, right? And we go through the network of these layers, and the last vector will be the one that we are predicting on. and kind of deriving this distribution. I'm sure you're familiar with the general machine learning concept and how does it differ from classical programming, but just to make further steps a bit more intuitive, let's just remind ourselves what are we doing in terms of machine learning or deep learning algorithms. So we are not incorporating any rules, right? So we don't know the relationships among the words and the output in the end. We know we have the data, a lot of text data, and we know the answers. We know what will be the probable word after this sequence. And we want the machine learning part is to understand these relationships and kind of tune different parameters to draw or estimate, approximate the function between these inputs. So in a classical programming way, we have to write a program, right, or write this relationship, this function. But in this case, we have just to show a lot of data and the answers. So in essence, if we take, for example, another task in image classification, so we trained a network, it kind of has these parameters tuned already. It understands, okay, these parameters mean that and that. But how does it work? Is that we input, of course, nowadays we use convolutional neural networks. We don't just stack the pixels in a row. However, the convolutional neural network extracts the information and it goes through the feed-forward neural network. And this scene. We calculate some parameters, right? At the beginning, they can be utter trash. It's just they're predicting something, and we now have to train a model to kind of make predictions better. So what will be the correct answer? The correct answer would be 2. But 2 has a probability after we apply softmax. It's kind of softmax is a function that kind of pushes the numbers between 0 and 1 and add to 1, some normalized sum. And so the 2 will be a correct answer, but the probability there is 0.043, and we need 1 there. So what the training process is allowing us to, or what is it doing in the background, it kind of tries to minimize the loss between the predicted value and the correct value. So 1 minus 0.043, it has to be kind of closer together. And there's log loss or other calculations that allow us to optimize that. For example, in our case, right, we have a probability of 0.22 for dog, which is good, but we want it to be even maybe larger. And the cost function is just basically a log loss. And what do we need to do is, why do we need a number? So we have to do calculus, basically. We have to move in the minimum direction of the cost function or loss function. And how do we do that? We just calculate the gradients and move in the negative direction of the gradients and try to minimize the correct answer and the predicted answer. So this is the same in this case. We want to kind of find the function that combines our input and output. At the beginning, it's just utter trash. It doesn't know the correct function. But after we minimize and update the weights and minimize the loss, and again, we'll try with new weights and minimize the loss, we kind of push these weights in the right direction and construct the function between inputs and outputs. So we were here. We already understood how to input our words. What do we need to do next? We have to understand what is the order of the words. Because in recurrent neural networks, it was easy, right? It was just time-stamped. So every word came one by one, and we knew the order of the words. Now we are parallelizing sequences, and we have to know where do they come from, where the words are how the words are ordered. This paper, Attention is All You Need, introduced a positional encoding algorithm that solved 4 problems. So what do we need from our positional encoding? 4 things, right? the position has to be unambiguous. So if it's one value, so it can't be another value for the next sequence. No, it has to be the zero, p0 is always like one value, right? The second one, it has to be deterministic. So we kind of have to know the relationship to kind of trace it back. So, okay, this was the first position, and we know the formula how to get the position, extract that. Third is, it would be beneficial if we knew the distance between the words. So the positional encoding should kind of incorporate this distance information. And third, if we trained our model on specific sequence length and position is very strict, then it will be a limitation for us to kind of add different sequence length, different length of different sequences with different lengths in the future to our model. So it could be flexible in terms of sequence length. And the paper introduced a formula that solved all these 4 problems. And of course, we know that sine and cosine are periodical functions. They can be determined, traced back, right? We can estimate the distance, and everything was clear in that case. Just to note that every position for the sequence, for the first element of the sequence is the same. And if we go back, you are adding the positional vectors to our embedding vectors, not concatenating, because it will add dimensions, right? So we had 5, 12 in this paper, so it will add another 5, 12. No, we don't want that. We will add the numbers and add the vectors. And how do we calculate them? We use sine and cosine to calculate the position, and the first element is always the same. These are the same vectors, and then the elements are based on the formula. But this is even not so important. The important is intuition. What are we trying to establish here? So, for example, the left D model is our sequence, right? The sentence. And we want to word every element, where is it, and how can we determine its position and its distance. So the sine and cosine, the periodical nature of the function, allows us to do these every 4 thing. Like, we can estimate the distance because we know that they repeat itself, right, after some periods. And then the length of the sequence, it doesn't matter, because again, they repeat. The periodical nature of the sine and cosine allows us to kind of be flexible in terms of this sequence length. So this was solved, and now we don't need to process words one by one. So we can just incorporate these positional encodings to our embeddings, and this will be learned during the process, and we already know the order thanks to that. Let's move on to the multi-head attention. And again, another shout out to MIT researchers who have made a lot of educational materials, courses on deep learning for free, and this is their kind of one of the courses, but maybe it's already outdated, and they publish new courses all the time. So and this is the example that is taken from their one of the courses. We have to introduce some kind of attention. So we incorporate positional encoding. We know the order of the word. We have the semantic vectors, right? And now we want to understand how the words are affecting each other. And this is the notion, this is the concept of self-attention, which has 3 distinct new kind of matrices that are called query, key, and third one will be derived from the queries and keys, where the query and key are multiplied with each other, matrix multiplication, and well, basically the dot product, which helps us to understand the similarity of the vectors. We will see the formulas in a couple of minutes, and we kind of see the similarity. And the value will become this output. So the third matrix, or the third set of parameters, will be the storage of this information based on one matrix that asks the question, another matrix that kind of knows the answer, and the value will be the third matrix that we use to tune our parameters. And to come back to our example, so the sentence which had these embeddings, right? So we have 8 tokens. Again, it's a simplified version. Tokens should be some subsequences. We have these embeddings, and we multiply these embeddings with weight matrices, just random weights. And as we saw previously, we don't know the weights at the beginning. If we're training from scratch, they're just random numbers that we're trying to update based on the loss that we are trying to minimize. So we calculated the gradient, right, based on current parameters, and we are moving in the direction of negative gradient and updating our weights as we go. So we need to know the correct answers for that, because we have to compare the predicted value and the ground truth, right? So we want, in attention mechanism, we introduce one matrix for weight matrix for the query. And what it does is basically goes through every matrix of a key. So we have these 2 sets of weight parameters, and we kind of calculate the scores, and not just one matrix and another matrix, but we want to find the similarity between matrix. And why do we do that? What does similarity mean in terms of our vector representations? So as you may remember, the dot product, cosine similarity, and other these things can be described as vectors pointing in the same direction or perpendicular direction, right? It will be 0, and or the negative direction. So that's why we are kind of comparing the keys and the values, the queries and the keys, and calculating these attention scores as we know them. And we will have some larger numbers for some relationship and smaller numbers for other relationships, but the numbers will be some from 0 to positive infinity. And we need again to kind of estimate the probability, and we use again softmax for that, which kind of takes normalizes it from 0 to 1 and sums it to 0. And as you can see, so some larger numbers will have a larger effect and will produce a larger probability. So this is the part of calculating the attention score inside these self-attention blocks. After we have these attention scores calculated, we kind of need other third matrix, right? Third set of weights, I would say. So the amount of weights, for example, in GPT-4, it's not published, so we can't know for sure, but some conferences, some information leaked that the number of parameters is trillions, some 1.8 trillion different parameters. So that is what is meant by these parameters. So we incorporate for every sequence, there's so many set of new matrices and parameters that we need to tweak along the training process. And the value matrix, it kind of aggregates the information and kind of stores the correct answer, and we apply it after we have these attention scores. So one little notion that was mentioned in the paper, that they just scale it by the dimension of the vector, but it's just for efficiency. It's not something to talk about in a longer term. So 3 matrices are introduced, and this is what we call an attention, a self-attention, where we have the input, we calculate the attention scores, the weighted attentions, right? And then we apply another set of matrices as values. And in the original paper, there were 8 of these blocks, as we saw in the beginning. So it's not just, oh, it goes through and I already know something. No, it needs a lot of a lot of layers, a lot of compute to run it back and forth to kind of incorporate context, incorporate the relationships and attention among these inputs. This is just a last part, sorry. This is just to show that how are these outputs kind of concatenated. So after we calculate the attention scores, we apply softmax as we saw it, then we apply another matrix to the resulted, and we have these kind of outputs of our self-attention blocks. And these self-attention blocks could be several numbers of them. So for example, in the initial paper there were 8, and we will have these outputs from each of 8 attention block, and we concatenate them and again apply another weight matrix at the end, and these are the set of weights that we are going to train. And what are the labels in this case that we're training on? For example, for our task. So this is quite a useful way of thinking about it, and for one sentence, for one sequence. So we have this long sequence and want to predict the last word. However, we can use the shorter sequences from the same sequence, subsequences, and again predict the next word. And it will kind of, from one example, it will generate several more. And it also excludes the necessity of labeling. Right? And so the pre-training process on text is utilizing this kind of concept of predicting the next word of the sequence based on sub-sequences. And well, at some point in chat models, you need human feedback and how did they call it, reinforcement learning with human feedback. However, in some cases, or in this case, you don't need human feedback for this pre-training phase to predict the next word, which is quite efficient. And but there's one problem that we will showcase here. Again, the initial paper states that on the other part of the architecture, which is the decoder part, there's a masked multi-head attention. Why so? Because after we have incorporated this information from keys and queries and values, we add a fresh set of input, like the parts of the sentences to the decoder part, but it already knows some information from the future, right? And we want to mask that information. We want the decoder part to only see the words that are coming in the subsequence matter, and doesn't see the one that comes from the left part, which is called encoder. So we use these kind of masks, and they're just an infinity element masks, which after the application of softmax just result in 0. So this is to prevent later tokens to influence earlier ones. Just to note that. We are slowly reaching the end, and I would like to talk a bit about the applications that, well, I'm particularly interested in from the medical domain, and these kind of large language models that are trained in this kind of manner, where you have a lot of parameters to tune. They're very powerful in terms of understanding general text and processing general text. But what about the medical domain? How can we trust these models to answer some diagnostic questions and kind of scale our medical practitioners? So Google is working on that problem, and they have developed a model called MedPol, which has already surpassed the approximate medical pass mark on US medical license exam. However, some of the research also show that GPT-4, that was not trained on the medical question and answering domain, just organically knew all the answer already, because the amount of data that they're trained on, the amount of parameters that they're scaling or optimizing is immense. However, new research show that new fine-tuned model of MedPalm-2 surpassed the GPT-4, but I need to update this information. Perhaps there are new models already available, and I will show some of the models today as well. So how do we train these models? So question and answers, right? So we want to like fine-tune these foundational large language models. They already know the, the context, the attention. This is already incorporated into the weights. And on top of that, they have general knowledge, right, in the last layers. So, but do they know the answers on the specific clinical questions? And as we saw, they're just generating the probability of the next word. So, and if the temperature or something is kind of a bit wrong, then it can cause a lot of damage if we trust them 100%, right? But we're kind of heading in that direction where we can fine-tune these models on specific domain. And MedPalm 2 and the documentation states that in addition to just these kind of general accuracies and other metrics, they also incorporate clinicians' reviews that go through the answers and kind of rate the likelihood of harm. Was there consensus in the literature or scientific literature or not? So it's getting much more kind of deeper. And this is one of the examples of the US medical license exam style question. So I don't know the answer. Well, I know because I looked it up, but I don't have the competence to answer these kind of questions. So how can I validate the large language model, right, to answer that? So the correct answer is B. Well, the current GPT-4 models produced a correct answer and correct explanation based on the exam evaluation. So again, if it does produce some correct answer, so maybe in some sense it is useful to incorporate these models and try to trust them even more. So in my domain in healthcare and AI in healthcare, the kind of healthcare moves or innovation in healthcare moves at the speed of trust. So, which is understandable. We can't rush things. However, we should kind of maybe ease into exploring the idea of integrating these unambiguous models, uncertain models that can sometimes hallucinate, but maybe in some sense there will be very, very practical. One of the repositories that has these medical large language models wanted to just share that already include that are from Google Research, DeepMind, and Harvard Medical School. They include these pre-trained large language models on the medical text. And Hugging Face is another resource that I would like to share, where these models are mostly based in. And in addition to models, they have these data sets and a lot of useful resources on the pre-trained transformers. The library is called Transformers Library, so I think the most popular place to look for pre-trained transformers. So you don't have to train these layers, 96 layers from scratch. You can use GPT-3, for example, which is open source. GPT-4 is not open sourced. However, there are a lot of models, for example, Llama, Llama 3 or other amazing models that are already open sourced. This one. So you don't have to train from scratch from the massive amount of text. However, you already kind of have an intuition how it's done. Every sequence has these 3 matrices, right? And the amount of layers can be very, very extensive. You have computational resources, yeah, so it can be done from scratch. But I will definitely advise look at these pre-trained models and pick some open source models from there. Excuse me. No, the screen doesn't work. Okay, so for example, I have used the OpenBioLLM. They are the documentation is not great. Unfortunately, there are some screenshotted examples, which is very bad practice. However, they use the model or train the model to summarize clinical notes, to answer medical questions, clinical entity recognition. So this model already does these things. So probably would be beneficial to start from these pre-trained models and see if the task can be solved in this case. I'm ready for your questions. There's a lot to cover, and maybe you have some questions that we can discuss, and I'm happy to share my experience in using transformers. Thank you so much.
Thank you so much, ma'am, for the wonderful lecture. So any participant have any question? Yes. If you have any question, kindly write on the chat box or just ask. Okay, ma'am, one question from the participant side. What are the key roles of positional encoding in the transformer architecture?
Yes, let's go through that. So because we need to incorporate some kind of order of the words, so it's very important where did the word come from. For example, this in the beginning, this sentence that I showed, this one. So the it from one place or the it is from other place. For us to incorporate parallelization, we can't lose that information. Where did the word come from? Is it an adjective for a coffee mug or is it an adjective for a computer? So it's very, very important. And also, as I mentioned, this was the result of the understanding the relationship of the word to. So the thing that the positional encodings do, sorry, I have so many animations, it's hard to jump, but I will jump right here, is that for every element of the sequence, it kind of has the same positional encoding values, so the vectors, right? We had the embedding vectors, and now we kind of calculate based on the formulas, the position of this particular element. And we add these values to our embeddings. So we incorporate position in terms of these values, which will be the same for every element. And how do we calculate these values? We use sine and cosine to kind of precisely determine the positional encodings and values for the first element, then for the second element, for the third element of the sequence. And why is it important, or why does it work? Why does it work? Sorry, is that the sine and cosine, there's a lot of ways to encode position, but in terms of this paper, sine and cosine have this periodical nature, and we can always compare these positional encodings, like how far away are they from each other, the words, right? And where did they come from? Because it's deterministic based on this formula. So the positional encoding allows us to determine where did this word come from the sequence? Was it the first word or the 500th word? Where did it come from? It's very important concept.
Oh, thank you so much, ma'am, for this answer. One more question is that, ma'am, what type of challenges you have to face when you have to implement this problem in the healthcare, NLP problem in the healthcare?
Sorry, what was?
What type of challenges you have to face when you have to implement the healthcare problem in NLP?
Very important question. So so far we have been dealing with two problems in terms of data acquisition. Right. Well, when we use pre-trained models, there's another issue, but in medical domain, so we need to label our data. For example, for Parkinson's disease, I need to know who's who for my algorithms to work. And labeling is kind of expensive if we think about the competence that what competence do you need to label the data? It's not just, oh, this is a cat, this is a dog, and this is a truck. You have to have like a medical diploma. So it's very
Yeah,
expensive,
definitely.
and the patients, the number of patients is also less, so the models can be a bit skewed. We have to pick the correct metrics to develop these models. So the data is a bottleneck in some sense in terms of regulations. And in Europe, for example, we are very strict, have very strict regulations in terms of data privacy. So we have these roadmaps to obtain these licenses and to collect the medical data from patients, and sometimes it takes months to have this kind of 10 patients data. However, you can't do anything with 10 samples. So this is one of the bottlenecks. And another one is interpretability, right? I have an
Another
interesting
one is what?
example I would like to show just in a second, interpretability wise, if you will allow me.
Yeah, I'm sure.
So interpretability wise, let's take a look at this example. So we developed a model that was quite accurate in terms of determining who is who. Is it a patient or is it a healthy control? However, when we looked inside of the model and kind of visualized the predictions and or the, how do you say, the maps or the heat maps, right? What regions are the model found the most important ones. The first model that we looked in, it was, oh my God, it doesn't look at the spiral at all. It kind of looks outside of the spiral. It maybe hallucinates something, maybe it sees something there, but we can't use that model because the background is not relevant at all. And then we trained another model, which was as accurate as the first one. However, the predictions were far more intelligent, or the explanations of the predictions. And we discussed this notion with neurologists, and they said that, oh, that's actually can be interpreted in that sense. For the Parkinson's disease, for the patients, it's hard to slow down, or it's hard to end the sequence of writing or walking or something. They need a concrete stop. So maybe the end is important in this case. And for the healthy controls, they also found an interpretive way of interpreting the beginning of the spiral. So how the controls, healthy controls, hold the pen is important, and they kind of started with a more, I don't know, a smooth way, right? So what I wanted to say that we need these kind of explanations on top of our models for doctors to trust the algorithms. But as you saw, we have so many parameters in terms of transformers-based models. There are so many matrices that we need to tune, and 1.8 trillion parameters, or
Very
hundreds
true,
of
ma'am.
millions of parameters.
Very true, very true.
Yes. So we can't just pinpoint every little detail, and that is the issue. And I think that we have to kind of lessen the strings, especially in Europe. Like, let's trust them on maybe lower risk decisions, but not just binary, like no deep learning in healthcare, and that's it. That we will lose a lot of value in this case. Yes,
I think it
thank you.
depends on the problem no? It depends on the problem.
Yes,
According to the
yes,
problem, we have to change the task and the algorithm.
yes, exactly.
Yeah.
Yes.
Ma'am, one more question. I think this is the last one. How do transformer models handle long range dependencies in data? How do transformer models handle
Yeah.
long range dependencies in data? Yeah.
Well, the basic, so far the scaling worked, right? The larger the models, the more intelligent they were. So there is not much issue with this long dependencies. And again, the hardware is also developing further, and so based on these novel advancements in parallelization and these attention mechanisms, they incorporate this context quite well with long dependencies. Yes, there are some limitations, but so far the wall is not hit yet, and they're quite they jumped quite well from the previous recurrent neural networks, and this is not a big issue anymore, the long dependencies.
Okay, okay. Thank you so much, ma'am. Any participant have any question? Please ask. Okay, I think, ma'am, there is no other question. So thank you so much for this very informative session.
Thank you so
So,
much for
Dr. Nitin,
listening. Yes.
yeah,
And
Dr. Nitin,
I will
please
leave
continue.
my contact if anyone is interested in human motor function analysis and kind of these topics, and then I will be happy to discuss further.
Yeah, thank you so much, ma'am. Very informative
So
session.
much. Thank you so much. Have a nice evening, and
Yeah,
hopefully
same to you, ma'am. Same
we'll
to you.
continue the
Have a nice
discussion.
evening, ma'am.
Bye-bye.
Bye, ma'am. So, participants, I'm sharing the attendance link at 8 p.m. So, kindly fill that link. And we have the two type of attendance criteria. First, we have to collect the attendance from the Cisco WebEx, and the second one from the link side. So, thank you so much from our side. Thank you.
Thank you so much, all of you. We will meet tomorrow for other interesting sessions. Good night, all of you. Thank you so much. All may leave the meeting. Thank you. Thank you so much.